So, what do Godzilla and geometrically quantizing gravity have in common? We conjecture ahead!
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Now, full disclosure, this is a MacBook Pro. We want to be open and as transparent as much as we can. Alright, so what is Memes talking about? Now, you remember, for those of you that have been paying attention and dealing with all this crazy numbers and everything, I think you're going to like this. Okay. Remember how I said you're going to like tomorrow? Well, happy Mario Day, everybody. Oh, by the way, February 8th is Big G Day. Why? That's when I'm going to claim Thad solved for Newtonian gravity. I don't know. It's such a beautiful thing. I think this is where intuition of beauty comes in. Because what am I talking about? Okay, so for those of us that watched the magnetic constant video yesterday, this is mu naught. We have that set up utilizing our universal binomial factorization equation. So you get your primary reaction. This is basically a sphere times the boundary conditions, which for this, the boundary conditions that we use for the rest of the different constants in nature. How very fascinating. So basically that's Planck length times Planck mass all over the Planck charge squared. Cool. And then we have our terminal actions. All right, it's 1 plus. This happens to be Gr, which is basically the radius of the hyperbolic vortex, squared, divided by the square root of 2 pi times the inversion boundary right there. Again, Planck length, Planck mass times Planck charge squared. Okay, now, what's this? This is Big G, also known as Newtonian gravity. I'm a lifelong kaiju fan. I gotta give Godzilla a shout out. Why? Because I can. Why the heck not? But, oh yeah, this is where Thad first presented it in the video. Yeah. Oh, this is even more fascinating. Because you see Gr, but what's the difference between these? Alright, you got a sphere, you got the boundary actions. The primary action here is 1. Boundary actions. Oh, and 1 plus, what's this? We use the 4 primary answers to the hyperbolic vortex equation. That's the square root of that, times the inversion boundary. Oh. And basically we just square that, and then we get this. It's so fantastic. But, okay, so what am I talking about here? All right. We'll go to the gravitational constant. The gravitational constant, also known as the universal gravitational constant, the Newtonian constant of gravitation, or the Cavendish gravitational constant, denoted by the capital letter G. It is an empirical physical constant involving the calculation of gravitational effects in Sir Isaac Newton's law of universal gravitation and Albert Einstein's theory of general relativity. All right, so basically, we got these numbers. What do you got here? Mass 1 and mass 2. All right, f of 1 equals f of 2 equals g. Mass 1 times mass 2 divided by radius squared, aka the inverse square law. How very fascinating. But apparently, we actually had some new numbers, and somebody was nice enough to send Thad some new experimental data as well. So he was so happy when he figured this out. It's just so like, oh, it's good to be there. All right, so the number, as you all know, is what we're looking for here. All right, nutational constant of gravitation, 6.67430 with error bars of 1, 5, or 15. Times 10 to the negative 11 meters cubed times kilograms to the negative 1 times seconds to the negative 2. What the heck is that? We go to our friend Wolfram Alpha. Again, links are in the doobly-doo. So when we look up Big G, and we make sure it's a unit, okay, we get those numbers there. Do they give us a little bit more? No, they're only using the standard ones that we basically agreed upon. Okay, you've got those Newton squared meters per kilogram squared there. All right, that's cool. Hey, welcome, Whitechapel. I'm not saying this is history. Could be totally wrong. If it happens to be not wrong, I think it's pretty cool to be here. Just saying. But, Newton gravitational coupling. Oh, what's this? Mass -1. That means we put in the denominator. Time to the -2 and length time cubed. What do we have there? Oh. Length cubed divided by time squared divided by mass. That seems to be what Wolfram Alpha is telling us. We're looking for our dimensional ingredients for big G. And then basically we get this number anyway. But how do we get out a wee bit more? Well, my friends, we go to our friend, the hyperbolic vortex equation. Okay. Again, that's that 1 over x plus x cubed divided by 2 pi. And we set that equal to I raised to the I, so the imaginary unit, raising it to the imaginary unit, and then we raise that to the negative pi divided by 2. So over here, you get a big twist. Over here, you got a little twist going the other way. Oh yeah, and we need to subtract out the Planck mass gap here. Again, we'll get into how we get those extra digits and everything. It's a fascinating story for another day. Okay, so we got our 4 answers here. Okay, so what do we do? Oh, I'm still using it. Oh, God. Oh, look, how very pretty. But, yeah. So we got J1, J2, J3, and J4. These are in the reverse order. Basically, one of these is negative, the other's positive. Okay. So, utilizing the universal binomial factorization equation right here, we'll toss on the Wolfram Alpha. We get this big crazy thing. We're going to break it down. Okay. So again, primary action is 1. These are our boundary conditions or our dimensional ingredients for our realm of persistence. And we get our terminal action over here. So that's that 1. Plus, the way I set it in here, I'm going to explain. Because the way it's listed for notation shape is J(r) raised to the 4th divided by 2 pi. Okay. So that's J(r) to the 4th again. We squared it yesterday because we were taking the square root of 2 pi, which we have there. And we have the inversion boundary, which is, again, Planck length times the Planck mass divided by the Planck charge squared, which equals 10 to the -7. Cool. All right. And we're going to break this down a little bit more. Okay, so what is this? So to get what we had in the picture here. Okay. So this is big G equals to, again, the ingredients, the terminal action. This is J3 and J4. We multiply those, and we divide that all by J1 times J2. I don't know. It sounds kind of like a Dr. Seuss book to me. Oh, God. Do I need to become a children's author? I may or may not be interviewing one in the near future. We'll see. So where are we going? We're going back over here. Oh, yeah. Okay. So hyperbolic vortex equation. We have those 4 answers. When we plug them in here, J3 times J4 divided by J1 and J2 comes out to be this number here. Okay. So coincidentally, we can reformulate that utilizing J(r), which is, whoop, I'm going to reload the page. All right, so we swap over to trig form. Trig form. Okay, this is J(r) right here. It's the radius of the hyperbolic vortex. We plug that in over here. Oh, there we go. Raise that to the 4th, and we divide it by 2 pi. Oh, look at that number. 64.011. 64.011. 5434. 543. Oh, that appears to be the same number. A very interesting coinky-dink. But you want to know what's more fascinating? Remember, that's J1 times J2. How do we go from that to 2 pi? Well, my friends, when we oh, excuse me, that was the whole thing there. But coincidentally, when you multiply all 4 answers, yes, I was holding up 5 digits there, 4 answers to the hyperbolic vortex equation, it looks to be 2 pi. Wait a second, 6.28. Let's see if we have any potential closed forms. Oh, look! 2 pi! Oh, very fascinating. Okay, break it down. So, you got this crazy thing here. So, 1 is the primary action. Oh, very cool. Times our boundary conditions again. The Planck length cubed, all divided by the Planck time squared times the Planck mass. Okay. And we multiply by our terminal action here. That's the 1 plus, as we saw here, this is r squared. Oh, excuse me. R to the 4th. Oh my god, I'm going back to magnetism. Are they related? Let's see. Hey, welcome, wow. Thank you for joining. Okay. So we got this crazy number here, over there. So what I did is, we threw it into the equation here. Okay. So we've got r to the 4th, divide by 2 pi, and we multiply it by the inversion boundary, which is, again, Planck length times Planck mass, divide by Planck charge squared, and that equals 10 to the negative 7. So it's 10 to the negative 7, we can basically just divide by 10 to the 7. Because that happens to be mathematics, my friends. Again, not really a big math guy. I'm going to utilize a quote. True love, priceless. For everything else is Wolfram Alpha. And we get this number here. What is this number? All right. Let's go to our, let's see what we're looking for here. So we're looking for this number thingy. So 6.67. All right. 6.67. 403. Error 15. So 403. So 4. Oh, where are we? Numbers. Oh, excuse me. 430. Okay. 4308. Oh, with 15 the error bars there. Wait a second. That means I could go to a 4-5. I could go down to a 1-5. Now, my friends, that looks like a geometric derivation of big G, aka the Newtonian gravitational constant. Now, don't necessarily always geometrically quantify gravity, but when we do, it's freaking beautiful. Now, that's all I got for right now. We do have a special guest coming on tomorrow. May or may not happen to be the primary progenitor of Wolfram Alpha. Not saying that I booked Professor Wolfram. I may have booked Professor Wolfram. But that's all we got for right now. Peace out, everybody. Thank you for joining. Take care of yourselves. It's a crazy world out there, but I think the light is right around the corner. See you, everyone.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.